Good morning, everybody. Thank you for coming. I'm going to talk about my paper in this conference about 3D printing capacitive pressure sensing solve for anthropomorphic robotics. My name is Markellos Ntagios. I am a final year PhD student from University of Glasgow from the Bendable Electronics and Sensing Technologies group. The outline of the presentation is as follows. We're going to introduce the problem of robotics trying to navigate on unstructured environments such as forests, mountains. We're going to present as well the background on 3D printing sensors in state-of-the-art robotic systems. Then we're going to discuss about the system design and our approach to solving these issues. We're going to discuss about the fabrication process of this particular embedded capacitive sensor and the approach that we have taken in order to realize such a system. Afterwards, we're going to present the experimental data that we have acquired from the experimentation that we have done. I have seen in the past incredible agility from robotic systems that can actually do backflips or even dance, walk, or even parkour in some cases. But all this has been done in a controlled environment where the systems have absolute control. These demonstrations have been achieved due to the fact that engineers have absolute control of the environment and the systems have absolute knowledge about the state of the environment that are currently in. If we take these systems out in the world, we can see clearly they have quite a lot of issues when it comes to stability. And this is usually due to the fact that there is no feedback, tactile feedback, through the soul of the robotics and actually understand the terrain that they're currently working on. For example, this is the state of the art that we have in robotics, and it still has issues when it comes to exploring unstructured terrain such as a forest. Robotic system will never have the capabilities of exploring uneven terrains or unstructured terrains without tactile feedback. Tactile feedback through the soul will enable the robotic systems to understand the morphology, geometry of the terrain so they can take decisions in order to stabilize themselves if they step upon uneven terrain. As on lately, we have seen 3D printing has become one of the major contributors to advancing the state of the art in tactile sensing. 3D printing and embedded 3D printing with multi-materials has become one of the major contributors to tactile sensing. We have seen that most of the literature has been focused on tactile feedback on the upper arms, especially on the fingertips. This technology has enabled us to do custom designs and change the approach of traditional fabrication. Also has reduced the cost and the time of fabrication. 3D printing enables us to customize our designs, which means that we can use the same approach from upper arms also to be used for a foot. Most soles use simple fabrication techniques to realize the sensors, but most of the systems in the literature have problems when it comes to wear and tear. So our goal is to design a 3D printed robotic sole with embedded sensors. Our goal is to increase the compressibility of the sole for better shock absorption, increase robustness by embedding these sensing elements, use material that are durable over extreme forces. Our approach is to use 3D printing to achieve the above goals. We have designed a capacitive structure that is used as a pressure feedback and it's been encapsulated into the sole. Using a two-part rubber material as a dielectric, to increase the robustness, we have encapsulated that structure inside of TPU that was 3D printed as well. At the beginning we have 3D printed a flexible non-conductive filament as a base, and then we have 3D printed the non-conductive elastomer up to the height of the dielectric material. Then we have used EcoFlex mixed in 1:1 ratio. We have kept mixing the mixture for about 20 minutes, and then we have poured it into the structure. Through mixing, we have kept bubbles inside the structure, as you can see in figure B. After that, we have left the mixture to cure for 5 to 10 minutes. We are now able to continue the fabrication of the rest of the system. After curing of the dielectric, we resume the fabrication of the top electrode using a conductive filament. After finishing of the fabrication of the conductive filament, we have printed the rest of the top cover using a non-conductive filament. As a result, we have an embedded capacitive sensor used for shoal that has increased compression due to the bubbles that is inside the electric. And here we can see the experimental results. At first, we've done a dynamic response. At the beginning, we have loaded and unloaded a 5 kilo load onto the structure every few seconds. Figure A shows the response of the system. In figure B, we have repeated the same experiment with 10 kilos instead. The second set of experiments was to extract the static response of the system. In figure C, we can see the static response of the system up to 35 kilopascals. We can see there are 3 linear zones of the response of the sensor. The first one is from 0 to 8, the second is from 8 to 22, and the third is from 22 and above. To demonstrate the robustness of the system, we have stepped upon it, and here you can see the results of the response. To conclude the presentation, we have discussed about the background of this work, we have discussed about the design of the 3D printing sensor, we have presented the results. This approach can not only be used for anthropomorphic robots, but it can also be used as a wearable. We can even expand this process into realizing an entire shoe. We can even use embedded electronics to realize an entire smart shoe, for instance. Here I would like to acknowledge the Engineering and Physics Science Research Council UKRI, the CRC, Shadow Robotics Company, the University of Glasgow, and of course the IEEE. I would also like to thank you on attending my presentation on 3D printing capacitive pressure sensing sole for anthropomorphic robots. Thank you so much. Have a nice day.